Welcome to the deep dive. Today we're jumping into, well, what might be the single most important piece of math for the future of intelligence.
It's a big one.
It is. And this is all part of our series Inside Quantum AI, which is brought to you by the researchers over at Loop Quantum AI Labs. You can find them at loopquantum.ai.
Our whole goal here is to really unpack the bedrock, the mathematical foundation for this next generation of AI. And at the heart of it is the Schrödinger equation.
Just a single line of calculus that basically acts as a blueprint for what we're calling quantum native intelligence.
Exactly. But to see why it's so revolutionary, you have to remember what came before.
Right, the classical setup, the Newtonian world.
The Clockwork Universe, everything was seen as this giant, predictable machine. If you knew the position and the speed of every single particle,
You could, in theory, calculate the entire future. That was the whole idea behind Laplace's demon.
that was the idea, a perfect deterministic reality.
And then 1925 happened.
And that certainty just shattered. Erwin Schrödinger publishes his equation, and it completely replaces that deterministic view with probability.
So instead of a fixed path for an object, you get what?
You get the evolution of a wave function. We use the Greek letter psi for it. It's basically the quantum version of Newton's F equals ma. It's the ultimate instruction set.
Okay, so this wave function, it's often described as a cloud of possibilities, not like a solid little ball.
That's a great way to put it. It tells you where an electron might be. Never, ever where it is, for sure.
Let's get into the math a little bit, because this is where it gets really interesting for AI.
Yeah.
The equation uses the imaginary unit, I. Why is bringing an imaginary number into physics so critical?
That's the computational secret sauce. The presence of I means that quantum states don't just exist on a number line. They have to live in a much richer, complex valued space.
A Hilbert space.
A Hilbert space, exactly. And you need that complex space to allow for superposition. It lets the state hold this incredible amount of phase information. It's not just on or off.
And that's the direct link. That's the translation from a weird physics idea to actual machine intelligence.
Precisely. The fact that a particle can be everywhere at once until you look at it, that becomes your computational engine. That's superposition.
Which gives you quantum parallelism.
Right. A single quantum bit, a qubit, can suddenly process this astronomical number of possibilities all at the same time. It's what allows for things that sound like science fiction, like quantum tunneling.
Where a particle just appears on the other side of a solid wall.
Because there's a non-zero probability that it can, the math allows it.
It's the source of all those famous head-scratchers. Schrödinger's cat being both dead and alive until we open the box.
It is, and it drove people like Einstein crazy. He famously said, God does not play dice with the universe.
But the math held up.
The math held up, and now that very same math is the engine for a new kind of AI.
Because classical AI is stuck, right? It's binary. It's or this or that.
Yes, it's fundamentally limited. But a quantum native AI can take that dead and alive state, that superposition, and treat it as a single coherent unit of information. It's richer.
And that's why you get these huge speed-ups with algorithms like Shor's or Grover's.
It's a completely different way of processing reality.
So if the math is so perfect, if it describes this incredible computational power, why is it so ridiculously hard to build these things?
Because quantum states are almost impossibly fragile. The biggest enemy is something called decoherence.
The environment, basically.
Noise, any interaction at all. A little bit of heat, a stray magnetic field, a vibration, and poof. The quantum state collapses back into classical bits before you can get the answer. The magic is gone.
And I imagine there's a data problem, too.
A huge one, the data bottleneck. It takes a lot of work to encode all our classical data, our bits, into this quantum form, into qubits.
So if it takes you longer to load the data than to run the calculation?
You haven't gained anything. So we're developing new strategies, things like qubit lattices or FRQI, to make that transition seamless.
Okay, let's pull this all together. The Schrödinger equation basically handed us a new blueprint for reality. The universe isn't a straight, predictable line. It's a shimmering field of probabilities.
And we're now trying to build an intelligence that reflects that, one that operates on that same fluid evolution of possibilities.
Moving us into a second machine age where cognition itself mirrors the source code of the universe.
It's about building machines that think in terms of possibility, not just in terms of certainty.
Thank you for joining us on this deep dive. If this whole conversation about quantum parallelism and what you called the ghostly dimensions of data has sparked something for you, we really hope you'll listen to the next episode of the Inside Quantum AI series. It'll be made available on X.
And if you want to do more than just listen,
Right. If you want to be on the team that's actually building this next generation of AI, you can find out more and see how to join the research at loopquantum.ai.